Hiya! So in this video, we're going to look at another example of oriented vector spaces and orienting bases. And then, yeah, so we're going to kind of go over that a little bit more in depth. One thing I had forgotten to mention in the last video is, now, if we look at this, we have two different orientations, lefts and rights. But like I had kind of said in the beginning, it doesn't actually matter what we do with which one. In other words, if I had started off saying that my original basis was the right orientation, then all of these would have switched. So in other words, number one would have become a left orientation, number two would have become a right orientation, etc. So in other words, the only reason these are left or right is because our initial choice that our basis was a left basis. So the choice is entirely arbitrary. It doesn't really matter. So let's look at another example. 167, and here I have a basis EX, EY, EZ. And the matrix I have here, we're going to keep this very general. So this is less of an example and more of like a general study as to what can and can't happen. So here I have three, it's going to be 3 by 3, BX, BY, BZ, CX, CY, CZ. So we have this matrix. So we just said any of these kind of work. I don't really care. Just let this be some transition matrix. Here, our vectors A, B, and C, in other words, are given precisely by these three vectors. Plus B, AY, sorry. AY, EY, plus AZ, EZ. BX, EX, plus BY, EY, plus BZ, EZ, CX, EX, plus CY, EY, plus CZ, EZ. Okay? And there's three different cases for this determinant, right? So here I chose an arbitrary transition matrix, or arbitrary matrix, sorry. Now, if the determinant is greater than 0, this implies that these three vectors form a basis, right? So this gives us a basis, is a basis, and it has the same orientation as EX, EY, EZ. If, on the other hand, my determinant is less than 0, well, I still know it's a basis. It's still a basis. The only difference is that it has the opposite orientation. Now, since I didn't choose a transition matrix from basis to basis, I chose an arbitrary matrix. This determinant could be equal to 0. Now, if the determinant is 0, what this is saying, A, B, C are not linearly independent, and therefore they do not define a basis, right? Remember that if it's equal to 0, then it's not a basis. And therefore, they do not have an orientation. So this is the key part of this section, is that they don't have an orientation. So if I take some sub-bases, like if I take something that's not a basis, then I can't really define an orientation. So this really requires us to have an orientation. Another thing to kind of note is that I didn't really need these vectors to be orthonormal or not. They can just be any basis, and I'm kind of happy it doesn't really matter. So the big kind of point, like this is what, part 5? Yeah, we've gone through 5 parts just going over this thing. And the main takeaway from this is that there are exactly 2 orientations. So this is kind of the big thing, that there's exactly 2 orientations for any real vector space. And given a basis as a reference point, we can either have the same orientation or the opposite orientation. It doesn't really matter. And if 2 bases have the same orientation, then we can transfer from one basis to another via what's called a continuous transformation. In other words, we kind of saw we can either do a reflection or a rotation in 2 dimensions. Now, I won't go into full statements because it's out of the scope of this course. It gets really complicated, really hard. But we are going to look at 3 dimensions and kind of look at what happens there. In particular, if B and C are orthonormal bases, with the same orientation, then there's some axis V such that the transition matrix from B to C is given by a rotation. Now, this will be Euler's theorem, Euler's theorem. We're going to see this later on. Potentially, is it even today? Is it today we're going to see this? No, we're going to see this next week. So don't worry about it. But know that this does exist, and we will go over this kind of in next week's time. So for now, just know that we can go from one to another in a nice way. So I will end this video here. Next video, we're going to talk about orientations of a linear operator rather than a vector space and kind of see what linear operators do in terms of orientations. So I will see you in the next video. Peace.